So part A is asking us for the maximum acceleration that can be placed on mass 2 without mass 1 slipping. So since it says no slipping, then the acceleration on mass 1 has to be equal to the acceleration on mass 2. So using Newton's second law, it's force is equal to mass times acceleration. So we're trying to find this acceleration right here. The force of friction is already given to us by the problem as the variable F. So that force has to be equal to mass 1 times the acceleration of mass 2, which happens to be equal to mass or acceleration 1. So moving this around, the acceleration has to be equal to the force of friction over mass 1. So the part B of this problem deals with simple harmonic motion, and what it's asking for is what is the greatest magnitude that this spring system can have before the mass on top starts slipping off the mass on the bottom. So this ties in with what we figured out in part A, which is the maximum acceleration it can have before it starts slipping. Right. So if you think about the system, the maximum force that's applied by the spring is when the spring is most compressed or when it's most stretched, when it's the farthest stretched out. So we can set the x of the spring equation, where force of a spring is equal to kx, and you can set that x as equal to a, or for amplitude. So the spring constant times the maximum amplitude when the spring is applying the most force on it has to be equal to the force applied to the system, which is the mass times the acceleration, which we got right here, F over mass 1. Alright, so plugging in mass 1 plus mass 2, we have to use the entire mass of the system, because the force being applied by the spring goes onto the entire system, and the acceleration is according to that. So mass 1 plus mass 2 is equal to m, and there we go. So we have spring constant times the amplitude is equal to quantity mass 1 plus mass 2 times the force of friction all over mass 1. And then you move the k over here, and then you get the amplitude is equal to quantity mass 1 plus mass 2 times F, force of friction, all over mass 1 times the spring constant. There you go. So for part C, it's asking us to describe the force of friction between M1 and M2 as it's being released from the maximum amplitude which we found earlier. So at point B, the force of the spring acting on the two masses will be at its greatest, because it's stretched out to the maximum amplitude of the sinusoidal function, which describes the position of the spring system. So at point B, which we're going to call the maximum amplitude, the force of the spring will be at its highest, which means that at that point, as soon as it's let go, the acceleration of the objects will be highest. As we determined earlier, acceleration of the top and the bottom has to be the same. So that means the force of friction has to be in some way related to the force of the spring. So that means the force of the spring is directly related to the force of the
friction. So as soon as the masses are let go from point B, the force of the spring gonna start up here at its maximum, and it's gonna start decreasing. And as that decreases, the force of friction will also be decreasing in a similar fashion. And then as it hits the point of equilibrium, the force hits zero, and it starts going to the negative direction. So that means in a similar graph right next to it, if this were the force of the spring, then the force of friction would also be in a similar manner. However, it would be opposite the direction of the force of the spring, so it would be something like this. Because once it passes the point of equilibrium, sorry, camera focusing, once it passes the point of equilibrium, the spring is going to push the other way. That means the force of friction is trying to stop it, so it's going to be in another direction. Part D1 asks us, determine the acceleration of m1 at the instant the masses are released. So it's talking about the point B, which we described earlier as the maximum amplitude. So that means at that point, the force of friction is going to be at its max, so we can use F again to describe the force of friction. And since at that instant, that's the only force acting on M1, because the spring is pulling on M2, and the friction on M1, between M1 and M2, is the only thing that's moving M1. So that means F is equal to M1 times the acceleration, which is the Newton's second law. So you can just say acceleration is equal to the force of friction over mass 1. And that's part A. Easy. So for part 2, it's asking us to describe the acceleration of mass 2 right after the moment that it's released from point B. So we know at that point that the force of the spring is going to be equal to, sorry, camera, come on, focus. The force of the spring is going to be equal to kx, and then the only other force acting on M2 will be the force of friction from M1, because since the force of friction is acting on M1, it has to be acting on M2, equal and opposite forces or reactions, Newton's first law. Alright, so kx minus F is going to be the sum of the forces, and then we know that the sum of the forces is equal to the mass times acceleration, Newton's second law. So we're going to say the sum of forces over M2 is equal to the acceleration, and then for that it's which is also equal to kx minus F all over M2.